ਸਤਿ ਸ਼੍ਰੀ ਅਕਾਲ, good morning, good evening. Same ਜਿਹੜਾ ਜਿੱਥੇ time zone ਹੈ ਉਹ ਸਭ good evening. And we are on a chapter number 2, algorithms and Turing machines. Topic is background to the algorithm concept. What precisely is an algorithm or a Turing machine or a universal Turing machine? Why should these concepts be so central to the modern view of what could constitute a thinking device? Are there any absolute limitations to what an algorithm could in principle achieve? In order to address these questions adequately, we shall need to examine the idea of an algorithm and of Turing machines in some detail. In the various discussions which follow, I shall sometimes need to refer to mathematical expressions. I appreciate that some readers may be put off by the such things, or perhaps find them intimidating. If you are such a reader, I ask your indulgence and recommend that you follow the advice I have given in my note to the reader on page number 8. The arguments given here do not require mathematical knowledge beyond that of elementary school, but to follow them in detail, some serious thought would be required. In fact, most of the descriptions are quite explicit, and a good understanding can be obtained by following the details. But much can also be gained even if simply skims over the arguments in order to obtain merely their flavor. If, on the other hand, you are an expert, again ask your indulgence. I suspect that it may still be worth your while to look through what I have to say, and there may indeed be a thing or two to catch your interest. The word algorithm comes from the name of the 19th century Persian mathematician Abu Jafar Muhammad ibn Musa al Khwarizm, who wrote an influential mathematical textbook in about 825 AD entitled Kitab al-Jabr wal-Muqabla. The way that the name algorithm has now come to be spelled rather than the earlier and more accurate algorithm seems to have been due to an association with the word arithmetic. It is noteworthy also that the word algebra comes from the Arabic al-Jabr, appearing in the title of his book. Instances of algorithms were, however, known very much earlier than Al-Khwarizm books. One of the most familiar, dating from ancient Greek times, 300 BC, is the procedure now referred to as an Euclid's algorithm for finding the highest common factor of two numbers. Let us see how this works. It will be helpful to have a specific pair of numbers in mind, say 1365 and 3654. The highest common factor is the largest single whole number that divides into each of these two numbers exactly. To apply Euclid's algorithm, we divide one of our two numbers by the other and take the remainder. 1365 goes twice into 3654 with the remainder of 1924. No, 924. We now replace our original two numbers by this remainder, namely 924, and the number we just divided by, namely 1365, in that order. We repeat what we just did using this new pair. 924 goes once into 1365 with a remainder of 441. This gives us another new pair, 441 and 924. And we divide 441 into 924 to get the remainder 42. And so on until we get a division that goes exactly. So then it's the last number they divide is by 21. That is the required highest common factor because it gives a remainder of 0. Euclid's algorithm itself is the systematic procedure by which we found this factor. We have just applied this procedure to a particular pair of numbers, but the procedure itself applies quite generally to numbers of any size. For very large numbers, the procedure could take a very long time to carry out, and the larger the numbers, the longer the procedure will tend to take. But in any specific case, the procedure will eventually terminate and a definite answer will be obtained in a finite number of steps. At each step, if it's perfectly clear cut what the operation is that has to be performed, and the decision as to the moment at which the whole process has terminated is also perfectly clear cut. Moreover, the description of the whole procedure can be presented in finite terms, despite the fact that it applies to natural numbers of unlimited size. The natural numbers are simply the ordinary non negative whole numbers 0 to probably infinity. Indeed, it is easy to construct a finite flowchart to describe the full logical operations of Euclid's algorithm. It should not it should be noted that this procedure is still not quite broken down into its most elementary parts, since it has been implicitly assumed that we already know how to perform the necessary basic operations of obtaining the remainder from a division for two arbitrary natural numbers a and b. That operation is again algorithmic, performed by a very familiar procedure for division that we learn at school. That procedure is actually rather more complicated than the rest of Euclid's algorithm, but again, a flowchart may be constructed. The main complication results from the fact that we would be using the standard denary notation for natural numbers, so that we would need to list all our multiplication tables and worry about carrying etc. If we had simply used a succession of n marks of some kind to represent the number n, for example, 5 dots to represent 5, then the forming a remainder would be seen as a very elementary algorithmic operation. In order to obtain the remainder where a is divided by b, we simply keep removing the succession of marks representing b from that representing a until there are not enough marks left to perform the operation again. The last remaining succession of marks provides the required answer. For example, to obtain the remainder when 17 is divided by 5, we simply proceed by removing successions of 5 marks from 17 marks as follows. They have a beautiful picture over there. And the answer is clearly 2, since we cannot perform the operation again. A flowchart which finds the remainder in a division achieved by this means of repeated subtraction can be given as follows. To complete the entire flowchart of Euclid's algorithm, we substitute the above chart for forming a remainder into the box at the center right of our original chart. This kind of substitution of an algorithm into another is a common computer programming procedure. The above algorithm for finding a remainder is an example of subroutine. That is, it is an algorithm which is called upon and is used by main algorithm as a part of its operation. Of course, the representation of the number n simply as n sports is very inefficient when large numbers are involved, which is why we normally use a more compact notation such as the standard system. However, we shall not be much concerned with the efficiency of operations or notations here, We are concerned instead with the question of what operations can in principle be performed algorithmically. What is algorithmic if we use one notation for numbers is also algorithmic if we use the other. The only difference lie in detail and complication of two cases. Euclid's algorithm is just one among the numerous, often classical algorithmic procedures that are to be found throughout mathematics. But it is perhaps remarkable that despite the ancient historic regions of specific examples of algorithms, the precise formulation of the concept of a general algorithm dates only from this century. In fact, various alternative descriptions of this concept have been given, all in the 1930s. The most direct and persuasive of these, and also historically the most important, is in terms of concept known as a Turing machine. It will be appropriate for us to examine these machines in some detail. One thing to bear in mind about a Turing machine will be that it is a piece of abstract mathematics and not a physical object. The concept was introduced by the English mathematician, codebreaker extraordinary, and seminal computer scientist Alan Turing in 1935 to 36 in order to partially in order to tackle a very broad ranging problem known as Anschauung's problem. Anschauung's problem, partially posed by great German mathematician David Hilbert in 1900 at the Paris International Congress of Mathematicians, and more completely at the Bologna International Congress in 1928. Hilbert had asked for no less than a general algorithmic procedure for resolving mathematical questions, or rather for an answer to the question of whether or not such a procedure might in principle exist. Hilbert also had a program for placing mathematics on an unassailably sound foundation, with axioms and rules of procedure which were to be laid down once and for all. But by the time Turing produced his great work, the programmer had also suffered a crushing blow from startling theorem proved in 1931 by the brilliant Austrian logician Kurt Gödel. We shall be considering that Gödel theorem is and its significance in chapter 4. The problem of Hilbert's that concerned Turing went beyond any particular formulation of mathematics in terms of axiomatic systems. The question was, is there some general mechanical procedure which could, in principle, solve all the problems of mathematics one after the other? Part of the difficulty in answering this question was to decide what is to be meant by a mechanical procedure. The concept lay outside the normal mathematical ideas of the time. In order to come to grips with it, Turing tried to imagine how the concept of a machine could be formalized, its operations being broken down into elementary terms. It seems clear that Turing also regarded a human brain to be an example of a machine in his sense, so whatever the activities might be that are carried out by human mathematicians when they tackle their problems of mathematics, these also would have to come under the heading of a mechanical procedures. While this view of human thinking appears to have been valuable to Turing in the development of his highly important concept, it is by no means necessary for us to adhere to it. Indeed, by making precise what is meant by a mechanical procedure, Turing actually showed that there are some perfectly well defined mathematical operations which cannot, in any ordinary sense, be called mechanical. There is perhaps some irony in the fact that this aspect of Turing's own work may now indirectly provide us with a possible loophole to his own viewpoint concerning the nature of mental phenomena. However, this is not our concern for the moment. We need first to find out what Turing's concept of mechanical procedure actually is. Let's read out Turing concept next. Let us try to imagine a device for carrying out some finitely definable calculation or procedure. What general form would such a device take? We must be prepared to idealize a little and not worry too much about practicalities. We are really thinking of a mathematically idealized machine. We want our device to have a discrete set of different possible states which are finite in number. We call these the internal states of the device. However, we do not want to limit the size of the calculations that our device will perform in principle. Recall Euclid's algorithms described above. There is in principle no limit to the size of numbers on which that algorithm can act. The algorithm or the general calculation procedure is just same no matter how large the numbers are. For very large numbers, the procedure may indeed take a very long time and a considerable amount of rough paper may be needed on which to perform the actual calculations. But the algorithm is the same finite set of instructions no matter how big the numbers. Thus, although it has a finite number of internal states, our device must be able to deal with an input which is not restricted in its size. Moreover, the device must be allowed to call upon an unlimited external storage space for its calculations and also to be able to produce an output of unlimited size. Since our device has only a finite number of distinct internal states, it cannot be expected to internalize all the external data nor all the results of its own calculations. Instead, it must examine only those parts of the data or previous calculations that it is immediately dealing with and then perform whatever operation it is required to perform on them. It can note down, perhaps in the external storage space, the relevant results of that operation and then proceed in a precisely determined way to the next stage of operation. It is the unlimited nature of the input, calculation space, and output which tells us that we are considering only a mathematical idealization rather than something that could be actually constructed in practice. But it is an idealization of great relevance. The marvels of modern computer technology have provided us with electronic storage devices which can indeed be treated as unlimited for most practical purposes. In fact, the type of storage space that has been referred to as external in the above discussion could be regarded as actually part of the internal workings of modern computer. It is perhaps a technicality whether a certain part of a storage space is to be regarded as internal or external. There is a great picture over there for a Turing machine requires an infinite tape. Anyway, one way of referring to this division between the device and the external part would be in terms of hardware and software. The internal part could then be the hardware and the external part the software. I shall not necessarily stick to this, but whichever way one looks at it, Turing's idealization is indeed remarkably well approximated by the electronic computers of today. We are on page number 35 and then we will continue from here.